going to talk about a counting unit in chemistry, and this counting unit is called the mole. A mole is a very convenient counting unit that can be used to convert between masses and the number of particles. 1 mole of anything is equal to 6.022 times 10 to the 23rd items of anything. The mole is a counting unit just like 1 dozen is a counting unit that we're maybe a little bit more familiar with. When I ask you to go get 1 dozen donuts from the store, you would come back with 12 donuts or 12 items. If I asked you to get a dozen roses, you would get 12 of those roses. So a dozen is a common and convenient counting unit that we use in everyday life. Another example of that is 1 ton. If we're talking about a really massive truck, instead of using units of pounds, we might talk about units of tons, knowing that 1 ton represents a mass of 2,000 pounds. So again, today we're going to talk about a counting unit called the mole, and 1 mole of anything is equal to 6.022 times 10 to the 23rd items. So the mole is an incredibly large number to work with, but it makes sense to use such an incredibly large number when we're working with things in chemistry that are microscopic. When we talk about atoms and molecules, they're so small and they're so numerous that it makes sense to use a very large number to describe them. In class, we demonstrate the size of a mole with a couple of different visuals. One of the things that we do is I show you a beaker filled with water. The beaker filled with water represents what 1 mole of water would look like. And when you take a look at the beaker, it turns out that only a very small amount of liquid or water is in there, and it's approximately 18 milliliters of water that is equal to 1 mole. So in 18 milliliters of water, there's 6.022 times 10 to the 23rd molecules of water. Again, showing us that, first of all, molecules of water are very small, and secondly, that they're very numerous in the sample of water. The number 6.022 times 10 to the 23rd seems like it would be kind of a random number of items to equal 1 mole. But the reason this value was selected is because it turns out that there are 6.022 times 10 to the 23rd protons in 1 gram of protons. So to take a simple single unit of mass, which is 1 gram, to get to the basic unit of mass here, it would take 6.022 times 10 to the 23rd protons. Same thing with neutrons. 6.022 times 10 to the 23rd neutrons has a mass of 1 gram. You may recall from earlier science classes that we have said that the mass of 1 proton is equal to 1 AMU. Okay, I got interrupted for a second, so I paused the lecture. So let's go back here. We were talking about why 1 mole is equal to 6.022 times 10 to the 23rd items. And again, the number of protons that's equal to a 1 gram sample of protons is equal to 6.022 times 10 to the 23rd. And since a neutron is approximately the same mass as a proton, there are 6.022 times 10 to the 23rd neutrons in approximately a 1 gram sample of neutrons. We've learned in previous science classes that the mass of 1 proton is equal to 1 AMU. We also know that the mass of a neutron is equal to 1 AMU. And we've learned that the mass of an atom is equal to the number of protons in the atom plus the number of neutrons in an atom. So there's a pretty convenient thing that we're able to do off the periodic table, which is we can figure out how many grams are in 1 mole of anything just by looking off the periodic table. So for example, if we look at a hydrogen atom on the periodic table, the mass of hydrogen on the periodic table is listed as 1.0079. We have previously listed this in units of AMU. for atomic mass units. And while that is technically correct, there's another unit that we can use. We know that 1 mole of hydrogen atoms would have a mass approximately of 1.0079 grams. And therefore, we can write a conversion factor to show this. We can say that in hydrogen, 1 atom of hydrogen, there is 1.0079 grams per 1 mole. Now, if we take a look at another atom on the periodic table, let's take a look at atomic number 3. Look at lithium. If you look at the atomic mass for lithium, it is 6.941. Well, we use the units of grams per 1 mole. That means in 1 mole of lithium atoms, there is a mass of 6.941 grams. In other words, 6.022 times 10 to the 23rd atoms of lithium have a mass of 6.941 grams. So we'll be using this unit and this conversion factor of 1 mole to a specific mass many times during the course of the semester. I'm going to go ahead and erase this space a little bit so that we can look at another way to kind of picture how big a mole is. So we have the beaker with water showing that a very small amount of water is equal to 1 mole of water molecules. The other thing that we like to do in class is we like to figure out the amount of time in years it would take the entire class to produce a mole of dots at the class rate. And so what we do is we have everybody get a pen or a pencil, and we're going to time ourselves for 10 seconds, and we're going to put as many dots in a box or on a piece of paper as we can. Okay? So we would go for 10 seconds and we'd say start. And everybody would put their dots on there. And I'm not going to do it for a full 10 seconds. I'm just going to give you the idea. And then after 10 seconds, what I would do is I'd say, all right, everybody count the number of dots that you have. Let's go ahead and multiply that by 6 so we can figure out how many dots we were able to do per minute. And then we added up everybody in the class. I went around and I said, how many dots did you get in 1 minute? How many dots did you get in 1 minute? And I went through the entire class and we added them all together, and we got a rate of how many dots we could do together as a class in 1 minute. And what we found in class is that we were able to get 7,000 dots in 1 minute. That is our class rate for making dots. So now what we're going to go ahead and do is calculate the amount of time in years it would take the entire class to produce a mole of dots at the class rate. So we want to figure out what our given is. Our given is a mole of dots. Okay, so we're going to take a mole of dots and we are going to find the value in years that it would take for us to create that. So I'm going to go ahead and set up a monorail again, where I have 1 mole of dots, which is always equal to 6.022 times 10 to the 23rd dots. And we're going to do a monorail, and we're going to convert from dots into years. So the conversion factor that we have is our class rate, the fact that in 1 minute we were able to make 7,000 dots. If I want to get rid of number of dots and I have that value in the numerator, I need to put number of dots in the denominator for them to cancel out. So I have 7,000 dots created in 1 minute by the class. And then now what I'm going to have to do is go from units of minutes to units of years, excuse me. So you can use whatever conversions make sense to you. You can do it in multiple steps. I would probably say that I know that there are 60 minutes in 1 hour, and then I know that there are 24 hours in a day, and we're just using an approximation here. We're not getting too fancy. We're going to say that there's 365 days in 1 year. And if we take a look at our units and see what's going to cancel, dots on the top and on the bottom cancels out, minutes on top and on the bottom cancels, hours cancel, days cancel, and we're going to be left in units of years. So we're going to go ahead and take a minute, and as always, we're going to multiply everything in the numerator and then divide by the product of everything in the denominator. So let's take a minute to do that. And what you should have gotten is 1.64 times 10 to the 14th years. Okay? So we're calculating the number of years that it would take the entire class to produce a mole of dots. So obviously a mole is an extremely large value that we could not even come close to making a mole of dots, all of us together, with 30 people in the classroom or 28 people in the classroom. If we did it our entire life, we wouldn't even come close to making a mole of dots. So that just shows you again how large a mole is. Let's do one more unit conversion having to do with a mole. If every single person on the planet, which at the time that we wrote this was about 7 billion, could eat one pizza every second, how many years would it take them to eat one mole of pizza? That is a lot of pizza. We're going to start with our given, which is 1 mole of pizza. And we're going to try to figure out how many years that would take. That's what we're trying to find. So we're going to start with our value of 1 mole, which is always 6.022 times 10 to the 23rd. So this is moles of pizza. Or I don't even need to write moles, I'll just write pizzas. And then what we're going to do is we know that the rate that we eat pizza is that we can eat 1 pizza every 1 second. That just sounds painful. So we've got 1 pizza per second. Now, once we cancel pizzas out and we get to seconds, we want to go from seconds to years. So let's go ahead and combine a couple of conversion factors. We know that there are 3,600 seconds in 1 hour, and that there are 24 hours in 1 day, and 365 days in 1 year. So let's take a minute to figure out how many years this would take. Again, we're going to multiply everything in the numerator and divide by the product of the denominator. And it looks like we get, we've got 2 significant figures here. We get 1.9 times 10 to the 16th years. Okay, so even if everybody was doing their part and eating 1 pizza every 1 second for their entire life, we would never even come close to approaching how long it would take to eat a mole of pizzas, because a mole is just that big. All right. Next topic here, last topic of the lecture, is the calculation of molecular mass. So in order to calculate the molecular mass of a substance, you simply have to count the number of atoms in each substance. And then what you do is you multiply the number of atoms in each substance by that specific element's atomic mass, and we add up all of the different products of our elements together. So we're going to take a look at the first example here, which is phosphoric acid, H3PO4. If we want to calculate the molecular mass of phosphoric acid, what we need to do is we need to look at the number of atoms of hydrogen. So hydrogen has 3 atoms. That's what the subscript 3 tells us. And we're going to take 3 and multiply it by the element's atomic mass off the periodic table. So for hydrogen, it is 1.0079. So we multiply that together, and then we're going to go ahead and add that to phosphorus. So I've got 1 atom of phosphorus. The atomic mass for phosphorus on the periodic table is 30.9738 grams per mole, or AMU. We're going to add that to oxygen. So we have 4 atoms of oxygen. We do 4 times the atomic mass for oxygen, which is 15.9994 grams per mole. So we go through and multiply that out. get 97.9951, and our units for molecular mass are grams per mole. So in 1 mole of phosphoric acid, there would be 97.9951 grams of that sample.